Hello, and welcome to Group B of the University of Stavanger's final presentation for the UiS for the robotics competition of 2021. The outline for this presentation is that you'll have the chance to meet the team, see our goals for 2021. We'll present our drilling assembly, the rig design and key systems, the bottom hole assembly and down hole sensor. We'll show how the different bits we've tried out have performed, the control system, and the hardware architecture finally. And here's the team. My name is Andreas. I'm the team leader of Group B, and I study first year of industrial asset management.
I'm Jon Erik. I'm assistant team leader, and I'm studying my first year on structures and materials.
Mine is Aslan, first year electrical engineering.
Magnus Ashton, lead mechanical engineer and first year student at the Industrial Asset Manager program.
My name is Kirishan. I'm the IT guy in robotics, and I'm studying first year of Industrial Asset Management Master program.
I'm Jonathan, the technical advisor. I'm studying the Marine and Offshore Technology first year of the Masters.
As robotics is becoming more and more known, we have tried to expand the organization. And as we're quite a lot of team members now with Group A and Group B, we've tried to develop a website that Kiri will mention a few words about.
Yes. The website's front-end style is following the UiS main page, and the backend is built with Drupal, which is an open source publishing system and framework. The reason for why we decided to create a web page in UiS style is to make it noticeable as a part of the university, and as well as robotics is not required to renew the server costs.
In the beginning of the year, we set ourselves some goals for 2021 that were supposed to be feasible with our year of studying and the time we could spare. And that was to improve the drilling assembly and the BHA design from 2020 after we've seen what worked and what didn't work. Remove all the unnecessary components on the rig. Implement a new hoisting system, going from 3 actuators down to 1. And to develop a custom printed circuit board with the same IMU as 2020 and try to work on that algorithm and code from there.
The drilling assembly is heavily modified this year. Here is a simple illustration of the drilling assembly with all the external parts included. The major changes is the hoisting system is replaced. More about this will follow in the presentation later. And the pneumatic motor is taken out of the BHA in order to shorten it. The pneumatic motor is the same as last year. Specs are here on the side. We move the motor up the drilling pipe, and to transfer the power, we use a steel wire as a flexible axle. The wire is put inside a terminal with threads on the ends, and the power is transferred through this and into the bit. We have also opted for using the top drive, which transfers power through the drilling pipe, so we can use both. The exhaust gases from the pneumatic motor is used to blow away the drilling debris and cool the bit during drilling.
Rig design. The miniature drilling rig was designed and manufactured for the 2017 competition. It has since then been reiterated and optimized each year to meet the new competition requirements. The rig was designed to replicate an actual rig with key systems such as hoisting system to provide the necessary weight on bit while drilling. Load cells is also induced to measure the weight on bit while drilling. This year the design have reduced the 3 actuators to a single actuator system, with a single servo motor driving the top drive and putting weight on bit. The bottom hole assembly for this year is based partly on the prototype from 2020. This was manufactured in stainless steel and were used in test drilling. It was, however, too large in size, which resulted in stock pipe. This year we went over to a much shorter 2-part BHA, an upper and a lower part. This was induced to minimize the risk for stock pipe and to increase the ability for directional drilling. This is the overview of our system. We have a prototype which is currently in manufacturing. It operates with a pneumatic motor which transfers torque through the drill pipe down to the axle and the bit. We have an integrated downhole IMU card down in the BHA sub. We also have a bent sub which will help the directional drilling. This system is completely encased, which will give maximum protection from the drill operation. And the difference in the actual downhole length has been reduced by over 70%, which also decreases the probability for stock pipe. The upper BHA can be seen in this image. We have the connection to top drive, the two-piece sleeve with assembling screws. We also have the wire assembly shaft where we can reach the wire, which goes through the drill pipe. Here we have the external and internal parts of the BHA sub. On the external side, we have two-piece sleeve, we have fluid ejection hole, assembling screws, and drill bit. On the internal part, we have the IMU slot, radial ball bearing, wire connector, axle, and dual truss bearings. The hoisting system for this year has been changed. The purpose is to add weight on bit and support the top drive. The main components is the channel support in aluminum, which also work as a cable run for powering and for fluid. The carriage can support up to 500 Newton plus a little extra with minimal deflection. It's powered by a Bosch brushless servo motor, and the carriage has a travel length of 1000 millimeters.
The rotational system for this year has two purposes, and it's divided into two components. One is the top drive motor, and the other is the pneumatic motor placed just below. We use the top drive motor to be able to drill a straight top hole section and a pilot hole, and also during directional drilling to sail or not drill inclined, just keep on going straight by making a larger hole, as we have a 8-degree bend in the BHA, which will obviously enlarge the hole when the whole system or the whole assembly is rotating. The pneumatic motor is used continuously throughout the whole operation, and its main purpose is to be able to directionally drill. So by rotating the pneumatic motor, the only part in the system that is actually rotating downhole is the bit. And that enables us to build inclination continuously. And by rotating the top drive, we can adjust the azimuth of the assembly and by just giving the drill pipe a few degrees of bend, it will try to turn to the side that we choose.
To speed up the prototyping and manufacturing process of the bottom hole assembly, we have utilized the 3D printers at the university, which allows us to do quick prototyping in materials such as ABS and PLA, which allows us the opportunity to verify the design before continuing. And for the parts in the BHA that is subjected to high stresses, we 3D print those in 17.4 pH stainless steel, which have higher mechanical properties than traditional 316 stainless steel. The only downside of using this 3D printed stainless steel is that the material is magnetic and interacts with the sensor data, but this is solved by demagnetizing before assembling. For the motor sleeve, which is under less stress, we used a composite material nylon with it reinforced with carbon fiber, which provide enough strength for during the drilling operations.
For the downhole sensor, we have used the same sensor as last year. It's the ICM 20948 from InventSense, which has 3-axis gyroscope, 3-axis accelerometer, and 3-axis magnetometer. It's connected to STM32, and it's programmed via the Arduino IDE for ease of use. You can see a picture of the current prototype in the top right. A new version is already in the works.
When it comes to drill bit performance, it's been important to us to ensure that we have the correct bit for the correct purpose. This is why we manufactured our own PDC bit together with Ling Drilling. It consists of 4 blades and 12 cutters, and has been designed in Inventor and 3D printed at the university. From our initial testing, we've seen that the inclination that we're able to build with the custom-made bit for directional drilling, is much better than it has been before. In addition, the hole quality has been improved a ton just because of the lowered vibrations during operation. The ROP is about the same as the bit we received from Baker for the inclination and directional drilling. But for the pilot hole section, we've seen that the UiS bit has been able to perform much better. We've tested all the bits together, as we can see on the next slide. And the main thing to look at initially is that the UiS bit built the same horizontal displacement as the Baker Hugh bit in about half the distance. This shows quite good potential for future tests, but unfortunately, when drilling with your UiS bit, the hole becomes exactly 38 millimeters, which is the outside diameter of the bit, and that causes the BHA to struggle to fit into the hole. But when we drill with the other bits, we have a lot more vibrations, which enlarges the hole and makes it easier to fit with the rest of the assembly. That is one of the main reasons that we've reduced the length and size of the BHA this year. The control system is based on the same architecture as it has been since 2019. It's based on a gRPC framework, and it's divided into layers and modules. On each layer, there are several modules, and each module can talk to each other. But the data only flows in one direction. So the data starts in the first layer and goes all the way through to the last, but it can't go back and forth. So when we start off with our data collection and it goes further to filtering, it can then be sent to the models, but it will not be sent back from there. And that makes it easier to implement the correct modules in the correct places and the correct layers. And I think this is a framework that we'll keep on using, as we're able to program each module in different programming languages, where we have most of the control system based on Python now. But we can choose to have some modules in Go or C++ or C# if we like that for performance reasons.
Hardware architecture. One of the wishes from the competitions earlier years was to able to rewire and get rid of some of the components that were no longer in use. And as you can see on the picture to the left, is the old system or before the rewire, and on the right is how it looks now. This makes it easier to add new components and troubleshoot, because everything is now collected into one enclosure. We don't need connectors from the main fuse box over to the box where we had the Arduinos. There's now just a hole up to it, so we can just run wires that way. And it also makes it safer because there's less risks of miswiring, because everything's more organized. And here you can see how the Arduino boxes looked last year. To the left, there were 2 boxes and a bunch of cables in the bottom. And on the right, you can see how it looks now, just a hole with the cables coming up into connectors, which are then going to the Arduinos.
Thank you for watching our presentation, and we're looking forward to the test drilling of the other universities and the Q&A. Thank you.